Hi guys, and welcome back to my channel. Today we're going to be looking at instantaneous power, and we're going to be focusing on how to derive instantaneous power from the basic principles using DC circuits. So let's get into it. So let's define what power is. So power is just the rate of doing work or the work per unit time, and instantaneous power is the power measured at a given point in time. So let's do an illustration of this using graph. So below here I have three waveforms of current, voltage, and power. So the red one represents voltage, and the blue one represents current, and then the other one represents instantaneous power, which is this graph here. So I have a blue line here, which has 3 points. Um, these points are representing current, voltage, and power at this instance. So this point is representing voltage at this particular point in time, and the value of current at this particular point in time is this here. So we all know that power is equal to VI. So when we multiply these two, we get value of power at this particular point in time, which will give us this value. And if you did a quick math, you'd see that the values of current and voltage are both negative. So when you multiply them, you're going to have a positive power. Okay, so let's consider two charged plates. Okay, so we have a positively charged plate on top and a negatively charged plate at the bottom. So when you have a charge associated with it as an electric field. Okay, so when you have any charge, whether it be positive or negative, around it will be an electric field strength. So you can consider this bar to be made up of positive charges and this negative plate to be made up of negative charges. So when you have two charges which are opposite, what you're seeing in between here are electric field flux lines that will be moving from the positive charge to the negative charge. Okay, so in between here you have an electric field strength. So since the top part is positive and the bottom part is negative, there is potential difference here between these two plates. So we want to see what the relationship between voltage and the electric field strength is. So voltage is just the integral of the electric field strength multiplied by the distance which is separating these plates. So this is the formula you're seeing here. Okay, this is vital in our derivation. Okay, so let us consider this setup here, where you have a resistor to which a voltage V has been applied to it. Okay, so since there's a voltage across this resistor, there's going to be current flowing through it. Okay, since the top part is positive and the bottom part is negative, we're going to have an electric field in this resistor. And since the voltage is constant, the electric field as well is going to be constant. So if we took out a small segment of this resistor, which is the segment from S to S plus ds, so the distance between these two ends of this segment is just ds. And when current is flowing through this segment, okay, there'll be charge flowing through it because current is just a flow of charge. So when you have charge in an electric field, it's going to experience a force. And this force is simply the charge times the electric field strength. Okay, so if the charge is experiencing a force, that means the electric field is doing work on the charge. So work is simply force times distance, and since we've already established what force this charge is going to experience, we just replace it in this equation and we have this expression. Okay, and we also want to know the rate at which this work is being done, and you know that the rate of doing work is simply power, and we already have the expression for work, and when we go ahead and plug it in, we're going to have this expression. Okay, so let us also remind ourselves that the flow of charge is just current, which is here, so which is just the q dt. Okay, so having established these three equations, we can proceed and finalize our derivation. Okay, so in this expression for power in that segment, we have the q dt in it, and the q dt in it is nothing but current. So we go ahead and replace the q dt with I, and we end up with this expression. Okay, so if we integrate both sides, we end up with the following equation, and this part is quite familiar because we saw it earlier when we were looking at the charged plates. So when we replace this expression with V, because V is equal to the integral of electric field strength ds, we have power is equal to Vi. So that's how you go about deriving instantaneous power. So I hope you found this video useful. If you did, please don't forget to like and subscribe.